So welcome to, I think this is our first PRECIP webinar of 2023. So PRECIP is the Process Study Model Improvement Panel, part of US CLIVA. So today we're going to hear from Kristen Rasmussen on the PRECIP project. And just for background, so some brief background on US CLIVA. The goal is to foster understanding and prediction of climate variability and change on intraseasonal to centennial timescales through observations and modeling, with an emphasis on the role of the ocean and its interaction with other elements of the Earth system. To serve the climate community and society through coordination and facilitation of research on outstanding climate questions, and also to coordinate and advance research within the US to improve documentation, understanding, modeling, and prediction of variations in global and regional climate. And so the PRECIP panel's mission in particular is to reduce uncertainties in general circulation models that are used for climate variability prediction, climate change projections, and this is all through an improved understanding and representation of physical processes governing climate and its variation. So our terms of reference, so we hold these webinars, we review, prioritize, and coordinate. We get information on relevant process studies, climate process teams, and other investigations. We're aiming for improved parameterizations and better quantification of model uncertainties. We develop and encourage mechanisms to further the development and implementation of timely and relevant process studies and a research strategy. And we advise US CLIVA on research priorities. We identify research gaps and develop suitable milestones to promote funding opportunities. And this is really, we're helping to foster and coordinate joint agency participation in supporting those activities. And we liaise with other CLIVA panels and working groups to ensure that model process studies and model improvement needs are considered in their efforts. So that is the job of our panel. And so part of our job is hearing about relevant process studies. So Kristen, I'm going to hand it over to you to present to us today on the PRECIP study.
Okay. You should be able to see, can you see my screen here in full screen mode? Okay, yes. Great. So I'm pretty new to this panel. I hadn't heard of it before you reached out to ask us about the PRECIP campaign. So I'm hoping that what I present today is relevant for this group. So today I'll be talking about the PRECIP Field Campaign. Our goals were to study heavy rainfall processes using an integrated and modeling and observational framework. Oops, excuse me. I'm trying to minimize this window here so I can see everybody. Okay, I think that's better. Okay, so first of all, I'd like to thank Michael Bell, who is the PI of the PRECIP Field Campaign. I work directly with Michael Bell at Colorado State University. And Rosamar Rios-Barrios is here on the call today. She's our modeling lead, and she's from NCAR. I also have a couple of contributions from several of my students that I'll share today. Okay, so the PRECIP Field Campaign, it's been a long journey. I'll talk about the timeline. But as a overarching view of what we did, we went to a moisture-rich environment. We basically went to Taiwan and southern Japan and brought the S-pole radar, the C-pole radar from CSU. We launched 4 times daily soundings, and we had a very coordinated approach over the region of Taiwan. We had a whole host of different universities, and I'll talk about those participants with some photos from our field campaign coming up. So why do we care about heavy rainfall? Heavy rainfall is a really important and very impactful extreme type of weather event. And these events seem to be increasing in frequency as we move in time. Here's an example of Hurricane Harvey on the top left, showing basically roads here in Houston. And then you can see on the right-hand side, basically the same roads, but as a result of Hurricane Harvey. So we actually covered a lot of these major roadways with an incredible amount of water. We've actually set a lot of rainfall records since 2017, and this is an outdated actually figure that a lot of these states are setting rainfall records. Globally, there's also been a lot of impacts with heavy rainfall. An example is the Bayou Front flooding in Japan in 2018. And just in the year of 2018, the 5 largest natural disasters in that year in terms of US billion dollars were a lot of basically all related to heavy rainfall with the exception of the Camp wildfire. So this is a big problem, and we expect it to actually change and be more impactful in a future climate. This is a study from my student, Aaron Doherty, showing we actually identified high resolution convection permitting regional climate simulations. We identified flash floods in these runs over the United States for 13 years in a current future climate, showing that the maximum rainfall intensity associated with flash flood rainfall is expected to be more intense relative to the current climate. If we look at this nice study here from Sukovich et al. In 2014, they basically show that if you look at the solid lines here, this is the top 1% and top 0.1% 24-hour accumulation by month. And the threat score, how well we can actually forecast these rainfall events, is on the y-axis. And you can see that the summer months, the times we have really heavy rainfall in the warm season in the United States, is our lowest predictability. We have the lowest amount of predictability in that warm season. And if you look at the dashed lines, our ability to predict this over years, that's shown in the top x-axis, has really not changed that much. We haven't made a lot of progress. I want to go back just for the purpose of this discussion here to frame our context and how we built the PRECIP Field Campaign. So there have been a lot of really high impact flash floods that had happened in the United States. An example is the Big Thompson flood. And so as a result of this, some historical studies looked at basically trying to understand what these flash floods had in common, right? We were getting these high impact events. They're trying to figure out what is the commonality here. And they realized that pattern recognition is a really important forecast tool because a lot of these systems are actually very, very challenging to forecast. And so pattern recognition, basically you're relying on forecast recall of previous rainfall events within specific synoptic and mesoscale environments, and an understanding of the rainfall climatology of the particular region. You need to understand spatial and temporal frequency distributions and the characteristics of these particular systems. And so it was found from a forecasting perspective that in general, these really heavy rainfall and flash flood events tended to be associated with convective systems that tend to be long-lived, quasi-stationary, or slow-moving, and basically passed over the same area for a long period of time. So this led to a really large advance in flash flood forecasting, this ingredients-based approach. And this is what we've based our PRECIP Field Campaign upon. This is from a Doswell et al. Paper in 1996 that states that many different types of these heavy rainfall producing storms, there's a whole wide range of systems that produce heavy rainfall. And so we should use pattern recognition and conceptual models, but they shouldn't be used in a vacuum. We should actually try to identify the key ingredients that support these different storms of different types. Okay, so I think I said that. Let me go here. This is the actual approach from the paper. It's very simple, where precipitation equals rainfall, average rainfall rate times the duration. So how long is the rainfall, and how heavy is the rainfall, and how long is it located in that location? They actually had a more complex version of this equation that basically laid out an essential set of ingredients for flash flood forecasting from this paper. You can see here precipitation on the left is equal to precipitation efficiency. You have here the liquid water density and the lower moist layer average air density. You have a water vapor flux term, and then you have a length scale. So the L sub S is horizontal scale, how large is the system, and then the C sub S is how fast is that system moving. This equation had been modified by Lin et al. In 2001 to take into account the effect of orography. So if you have the presence of a mountain in the region, you can take that into account by looking at this terrain height aspect and separating into environmentally forced vertical motion and the terrain height forced vertical motion in a more linear framework. Okay, but the key here is that a combination of ingredients produce conditions favorable for heavy rainfall, and we look at a wide variety of precipitation systems. It's not just one type of system producing heavy rain. We need to consider the whole spectrum. And so this is basically the conceptual diagram for our PRECIP Field Campaign framework, that we are using this ingredients-based framework to understand the combinations of rainfall intensity. You can see here it's strong vertical forcing on the y-axis with rainfall duration that has maybe more stronger horizontal forcing. And if you go in the diagonal up to the right, hopefully you can see my mouse, you can go up to the right here, and you can get to extreme rainfall through a combination of a lot of different factors. You can have very, very short duration, high intensity rainfall. We call these deep convective cores. I'll come back to this later. Or you can have much broader, wider systems that last for a really, really long time. These are oftentimes, large stratiform regions. And tropical cyclones is an interesting mix between all of these categories. So the primary objective of PRECIP, we built it on this framework, is to simplify the complexity of multi-scale interactions by identifying key ingredients and processes in the two limiting cases of high intensity and long duration events in a moisture-rich environment. Okay, a couple of notes for this particular panel on the scientific basis. We designed this campaign with an innovative way of trying to investigate the universal connections to the extreme rainfall problem by testing hypotheses that are not directed at any one specific weather phenomena. We were happy to see the whole spectrum of systems producing heavy rainfall. And that was one of our experimental designs that allowed for a great success, actually, with the data we did collect. This also maximizes the chances. We wanted to go to a moisture-rich environment to try to see as many heavy rainfall events as we could. And so we went to the moisture-rich natural laboratory of Taiwan. It's an extremely moist place. If you've ever been there in the summertime, the humidity there is incredible. It's a lot of humidity. But the interesting part is that even though they have among the most humid conditions anywhere on the planet, they don't always have heavy rainfall. And we wanted to understand if we always had enough moisture, what were the other processes that then led to the production of heavy rainfall when moisture was not one of the things we were missing. This also allows us to find the commonalities of heavy rainfall as well. And particularly for this panel, the integrated modeling and observational experimental design, we did this from the beginning. And I'll show you a couple of slides on this. We actually used OSSI's high resolution model simulations, basically over our region with the type of heavy rainfall system we were interested in, to actually design our radar scanning strategies to make sure that what we did receive when we collected that database, when we got that data back, that we would be able to answer the science questions that we had set out for from the beginning. And I'll talk about those details. Okay, so the timeline. This has been a very interesting project. As you can imagine, it happened, we planned it before, during, and after the pandemic. So just to give you a history, this basically started in 2015. There was a joint NSF MOST. MOST is the Science Foundation of Taiwan. So they had a joint workshop on extreme precipitation in Taipei that Michael was a part of. In 2016, there was a second US-Taiwan workshop on extreme precipitation in Honolulu. In 2017, we had our first PRECIP science workshop in Fort Collins, where we gathered our science team and we started talking about the proposals. Those proposals, the SPO EDO proposals, were submitted to NSF in 2018. And then in 2019, we had a science workshop at the ICMCS, the International Conference of Mesoscale Convective Systems, in Okinawa, Japan. And unfortunately, one of our science team members, Fuqing Zhang, passed away in that year as well. But he is part of our science design, and we have some members from his team actually all on our science team as well. In 2020, we had a March planning workshop at CSU. In early March of 2020, we'd made the tough decision to delay our field campaign. We basically had to push the button to ship our radars out to the field. We delayed, we had no idea it was coming. And so in that year, we did a pilot study where we actually deployed a lot of our modeling tools. I'll talk about those that were deployed by Rosamar and by Yunji Zhang at Penn State. And then in 2021, we made the decision again to delay because there's no way we could deploy radars out to Taiwan. So we actually did a local PRECIP campaign. It was a pre-PRECIP field campaign. It was local here in Colorado. We used the CHILL radar, the CSU Chivo radar. We launched a bunch of weather balloons. And so we actually had a complementary campaign here in Colorado in a continental, dry climate here that we can then use to compare with the observations we collect in Taiwan. No COVID-21 was our Taiwanese partners campaign. that they conducted in Taiwan in coordination with us. And we also did model experiments in this year over both Colorado and over Taiwan. And then finally, in 2022, we were able to do our field campaign. Okay, so I have this here mostly for information for later. These are our 4 hypotheses that drive our field campaign. What I'd like to highlight here is that H4, I'll come back to this one later. We're talking about different physical processes related to thermodynamic, dynamic, and microphysical processes related to heavy rainfall in the top 3 bullets here. The last one is basically looking at if we have significant reductions in model bias. We can do this through improved representations of those processes in the top 3 hypotheses that will then contribute to significant increases in forecast skill when coupled with improved representation of mesoscale structures that enable those processes to occur. And so we're working very closely with our modeling team. In fact, it's integrated into our science hypotheses for our field campaign, and we're working very closely with the team, as you will see in the slides today. Okay. So why did we go to Taiwan? Taiwan has a ton of heavy rainfall across the warm season of the year primarily. You can see here the green bar is where we actually conducted our PRECIP Field Campaign. And in these different histograms are basically when you get all types of heavy rainfall on the top left, tropical cyclone rainfall, frontal rainfall, this is basically Mayu front rainfall on the front part of the season. And then we have afternoon thunderstorms that happen throughout the summer. And so this is a moisture-rich environment, and they have very different types of modes of precipitation that happen throughout the year. And so we decided that this was a great target for our field observations. This is what our domain looked like here over Taiwan. We had 2 super sites, one over Hsinchu in Taiwan, and then also one over Yonaguni Island. It's the southernmost island in the Japanese chain. And on at the Hsinchu site, we had the NCAR S-pole radar. You can see a picture of it here on the top left. It was a great site, right on the canal, right on the water. We had some great views here, coupled with some super sites. We had astrometers, we had rain gauges. You can see all the different amazing platforms that are available in the Taiwan island. We also had a TMAR radar up to the north, coordinated with our Taiwanese colleagues. You can see the example here. On the top, we had micropulse dials. These were basically sampling low-level moisture variability at high resolution. In the boundary layer, we had 3 of those across the island of Taiwan. And then on the Yonaguni site, we had the CSU C-pole radar. It's a C-band radar. You can see it here on the right. We also had a Nagoya new pole and also a Ka-band radar on Yonaguni as well, connected with our Japanese colleagues. Okay, so NCAR S-pole, it's a really big radar. It's an S-band, very, very high quality polarimetric measurements. We can get retrievals and cloud liquid water from this. It's been deployed in many field campaigns in the past. C-pole is actually a recent radar that has been refurbished as part of a major research instrumentation award. It's a shipborne radar, but we actually mounted it on the ground. You saw an image of that on the previous slide, and it's had several successful deployments previous to PRECIP as well. Okay, so when we were designing the field campaign, we decided that we really wanted to sample the space across the central mountain range of Taiwan. You can see the topography here in the middle. Here's the S-pole site here on Taiwan. Here's a C-pole site over on Yonaguni Island. And when we did some radar beam calculations, here's on the bottom right, you see basically different elevation angles for each of our radars. What we wanted to do is make sure that our placement of our radars, our scanning, and our orientation and how we design this experiment would actually give us the information that we wanted to see. And so using this framework, we actually ran a case study, the Mayu Front on 2nd of June 2017. It was a record-breaking event in northern Taiwan. This is a high-resolution OSSI simulation that we used before we submitted our SPO EDO. And on the right-hand side, you can see basically that we used some software to look at our 2 sites and actually retrieve out of the model what we will see if we were sampling this exact event, what we would see from the radar scanning strategy that we had. And so you can see we have some really nice depictions of the different type of systems and the intensities across this space. We can characterize both upstream and downstream. We helped fill in some of these gaps on the east side of Taiwan by putting several other platforms over on this side. But we used these tools in the development of our field campaign plan. And I hadn't heard of many examples of this being done before the proposal was even being submitted. So this is one example of how we've tried to do this integration from the beginning. Okay, I'm going back to this hypothesis number 4. This is the connection to the model. And so Rosamar graciously provided me some slides here telling us about how we did this. So we had a very nice collaborative effort across NCAR, CSU, and Penn State for PRECIP 2022. And so we had global modeling with MPAS. So you can see this on the left-hand side here, where we had basically a 15-kilometer mesh that went down to a 3-kilometer mesh right over the Taiwan region, providing global modeling of rainfall from the NCAR team. In the middle, we had a really nice convection permitting WRF ENKF ensemble that included assimilating satellite radiances in real time, which is really exciting and has provided some really great improvements of our modeling efforts in this region. And then we are planning, and we are in progress of doing some large eddy simulations using CM1 on the right-hand side here. So there's this kind of integrated approach that had an operational capability that's then also translated into the research framework. Okay. So this is from Rosamar. This is the MPAS configuration. And so you can see that there's 15-kilometer spacing over the entire globe, with then 3-kilometer inner cell or inner spacing here centered right over the Taiwan region. We had daily 5-day forecasts provided from May 21st to August 10th. We did this in 2020, initialized with 12 UCC GFS model data. And then in 22, this was initialized with 0 UTC ECMWF integrated forecast system forcing. The global domain had a refined mesh of 3 kilometers over the West Pacific and was part of this multi-model convection permitting ensemble. Graphics from this were provided to the CWB, the Central Weather Bureau in Taiwan, and other of our partners in both Taiwan and Japan for prediction in real time. This is an example here, and we have some archives here that you can see if you want to go to the website on the bottom. But we have accumulated rainfall forecasts as an example on the left here, and an example of a simulated sounding that was derived from these MPAS runs. We had traditional output, and then Rosamar and her team worked very carefully with the science team to provide special metrics. We asked for specific things that would actually really help us with understanding what mode, in that spectrum were we seeing. How could we place it in our PRECIP framework and things like that. So we worked very carefully with them ahead of the campaign to build these metrics for maximum utility during the campaign this past summer. Here's another example. They had an experimental convective stratiform partition that was produced in real time with experimental MCS tracks from Kelly at NCAR. And so these are some example of these special products that were produced as part of this effort. Okay, and this is thanks to Yunji Zhang from Penn State University. He ran the WRF ENKF system for us. We ran it in 2020, 2021, and also in 2022. So you can see we had 3 times a real-time forecast. We have between 20 and 40 members from all of these simulations. This is a really exciting data set that we're just starting to mine now. We had real-time ensemble forecasts with high all-sky infrared radiances being assimilated in the real time. This is the first time this was done. And we think it's provided some enhancements and some improvements in the ability to simulate these mesoscale systems in this tropical environment. We also have corresponding forecasts over Colorado that we are doing comparisons with to see how this changed over a Colorado domain versus over the region of over Taiwan. And here's an example of some of the forecast products, some traditional output. So we have basically probably matched mean rain forecast on the left in that inner domain you can see here, centered over Taiwan, and probability of this OLR below 140 watts per meter squared on the right-hand side. Sorry, my video panel is kind of in the way. I'm going to try to move this. Oops, hide window. Okay, that's much better. Okay, so this is just some photos from our field campaign. We successfully completed the field campaign in summer of 2022, including lots of quarantine days for our team, between 3 and 7, actually 10 days for a lot of our team in quarantine in Taiwan. We were able to collect observations very successfully. Our timeline, we operated from May 25th to August 10th with SPOL, 78 days. So a really, really great data set. We had a 74-day data set from CPOL. We had 3 micropulse dials operating for 75 days. We had 660 PRECIP soundings, plus 681 TAHOPE soundings. TAHOPE is our partner project in Taiwan. So an incredible number of soundings from this team. And we actually had, because of the lack of helium available at the time, we were actually not able to order helium. So we actually used hydrogen, and we implemented safety procedures, and all were launched safely, and we were very proud of that effort. We also had 1 times daily NCAR MPAS simulations, 4 times daily Penn State WRF ENKF simulations for the entire campaign. And additionally, we had a daily GFDL shield simulation, 1 kilometer out to 15 kilometers global in the latter half of the campaign. So we have a lot of observations and then corresponding model simulations of different types and resolutions, and global versus regional as well. Okay. During PRECIP, we had 11 different intensive observing periods where we did see a wide range of systems. We saw Mayu front, so basically more synoptically forced types of systems over the region associated with the Mayu front. We had afternoon thunderstorms. We had some tropical cyclone that kind of came nearby. We actually had a sandwich between 2 tropical cyclones. We had different types of moisture. And so we actually did sample quite a wide range of convective systems during this campaign. Here's one example, the IOP1. This is the 26 May Mayu front case, where you see basically tons of rainfall over the region. Here's some information from SPOL, basically showing lots of interesting rain. We have a really nice depiction of the Mayu front in the frontal rain bands intersecting with the mountains here of Taiwan. Some vertical cross sections from the radar are shown here. You have lots of particles and all kinds of interesting things here in this data set that will allow us to understand these systems more clearly. We also had an interesting moisture surge in IOP 9, July 29th. So this is information from the micropulse dial at Ilan. This is the East Taiwan site. And you can see over time, this is a vertical, basically depiction of low level boundary layer moisture. And you can see the buildup of a lot of moisture moving into this moisture surge that led to some very interesting structures seen from Seapole on Yonaguni Island to our east. We had a lot of interesting events, not even on non-IOP days. This is an example. I was there during this particular case. Incredibly deep convective thunderstorms sitting over the Taipei Basin in the north part of Taiwan. Incredibly deep, really interesting structures, extremely high values of KDP, indicating really, really heavy rainfall rates. And I can confirm that I felt those at the surface. I was basically drenched walking to the CWB that day. We also had a typhoon sandwich where we were basically right in the middle of 2 typhoons. So we were influenced by the moisture being put into the environment from these 2 typhoons. We didn't have a direct landfall, but we were influenced by these 2 systems swirling around Taiwan. So there were some really interesting days, even outside of IOPs. Okay, couple key successes. This was a really challenging campaign to do. We had, as you saw the timeline, we had it funded ahead of the campaign. We had our grants funded right before the pandemic, and then the pandemic caused a 2-year delay. But we were really successful in continuing to build our international collaborations across Japan and Taiwan, despite this delay and the ongoing pandemic. We utilized our opportunities, and we collected really interesting data sets, both with the modeling efforts and then a local Colorado campaign as well. Our instrumentation all worked really well through the project, and we had a really unique experimental design with integrated and modeling and observational components. This is the first international deployment of the NCAR micropulse dial, the first land-based deployment of CSU Seapole, and we think that we may be the first NSF field campaign to use hydrogen extensively and safely for radiosonde launching. And so we've developed some safety documents based on our experience. We had a really significant education and outreach component with very diverse participation. We had 18 US students participating, both graduate and undergraduate students. We had 11 early career faculty and postdocs. 8 of those were female. That's pretty notable. Only 7 participants in mid to late career stages. We had a lot of Taiwanese and Japanese students participating. We had hundreds of visitors to SPOL and participated in lots of news articles, and we had a lot of Twitter social media presence during the campaign. Okay, I want to go through a couple quick examples in the last couple of minutes here. First example is an ingredient space framework and observation. So one of my students took this framework that I talked about at the very beginning, and we basically parsed this in TRIM precipitation radar observations. These are the different storm modes. I'm not going to go into these in detail, but basically we're looking for different vertical and horizontal characteristics of storm modes seen by the TRIM radar that map onto this PRECIP framework that we saw at the very beginning. If we look at where these different storm modes occur from TRIM observations, basically we see that across this region, it's very, very moist. There's a lot of precipitation, a lot of convection that happens, but you do see that there's some interesting characteristics here over the island of Taiwan. My student took a box basically right over Taiwan and calculated composites for systems that occur just in that white box over Taiwan that you see here of vertically integrated moisture divergence. And so what you see is that anywhere you see blue, we're seeing convergence of vertically integrated moisture. You see for deep convective cores, these tend to be a little bit more localized. We don't have as strong of values, but as you step to these wider and broader systems, wide convective cores are really big, more mesoscale convective system type structures. And then broad stratiform regions, you're actually starting to see something that looks kind of like the Mayu front actually sitting over this region. So you kind of require more organization, larger scale moisture convergence associated with these broader and larger storm modes on the lower part of the intensity spectrum in that framework. And we can confirm that with basically a time scale. So this is going back 7 days relative to the occurrence of that system and from TRIM. And you see that, you don't see much of a signal, maybe just a general signal with deep convective cores. But as you get to these bigger and broader systems, you see a very interesting ramp up of this vertical moisture flex and then a ramp down after the event. So these connections of the ingredients to these different storm modes is something we're working on with observations. An example, a second research example is thinking about this in model simulations. So because we didn't conduct this field campaign until just last summer, we took this same 2nd to 3rd June Mayu front case that I showed before, that we ran that Aussie simulation for before we submitted the SPO EDO. And we did a terrain modification experiment. We took the full topography of Taiwan, we reduced it by 50%, and we saw what happened to the orographic enhancements of these systems connecting to that objective number 3. If we look at the reflectivity Hofmahler, so time is going up on the y-axis, longitude is on the x-axis, you can see that there are some significant differences with the enhancement over the topography in particular of these reflectivity values. These are simulated radar reflectivity. If we look at a movie of storm modes, this is basically what the storm mode analysis applied to the model looks like, that with the same storm modes that we used with the TRIM observations. If we look at this in frequency differences, we can see actually we do see some really characteristic differences. We see significant reductions in deep and wide convective cores over the topography. We actually see interesting enhancements of the broad stratiform systems over the west side of Taiwan and over the mountains when we reduce the mountains. And so we're digging into some of these data sets using complementary frameworks to look at observational pieces and then also the modeling pieces as well. We see significant rain reductions when we do this as well. I forgot that last piece here. And so when we reduce the central mountain range, this leads to 50% less rain, weaker updrafts, and decreased convective activity over Taiwan. The third example is from Rosamar. This is a successful MPAS forecast from IOP2. Here's an example here showing the 24 accumulation ending on 12 UTC on the 31st of May. You can see this is here on the left. These are the observations, the radar QPE that are gauge corrected from the Taiwanese. And on the right-hand side, this is this MPAS-A forecast, 60 to 84 hour forecast of this same time period. And you can see actually fairly significantly similar rainfall amounts and rainfall patterns and locations from this particular event. So this was a nice success story. We did notice a lot of modeling challenges. So we had issues with precise timing and location of convective organization over Taiwan. This was not always accurate, and not even with convection permitting models. So that's something we noticed. All of the models seem to struggle with precise location of the subtropical high and how it modulated rainfall during the July and August months. Some of the Penn State WRF ENKF members had too much precipitation on the east-facing slopes of Taiwan, and the MPAS-A rain rate biases increase over time over the West Pacific Ocean. And so these are some of the things, the modeling challenges that we noticed. But again, we're working together across our modeling and observation teams to look at how we can not only understand these challenges, but maybe then improve things with the enhanced process-based understanding that we're gaining from our analyses. Okay. So in conclusions, we had an integrated modeling and observational approach that was really key in the PRECIP experimental design. We started that from day one. This has led to coordinated observations and modeling experiments over 3 years due to the ongoing due to the pandemic, and this has led to ongoing research efforts across these teams. The ingredients supporting these heavy rainfall systems build over long durations for these larger events compared to smaller events. We saw some interesting changes in when we reduced the topography, so that the connections with orographic rainfall is really strong in this particular part of the world as well. And I just wanted to comment that a very large and coordinated model and observational data set is available for use by the community interested in heavy rainfall in Taiwan and Japan, and also a corresponding data set in Colorado if there's any interest. Okay, with that, I will take any questions. Thank you for listening.
Wonderful. Thank you, Kristen. So let's open up the floor to questions.
Oops.
Colin, you have your hand raised.
Colin, you're on mute.
I can't hear you.
You might need to change your microphone setting on the WebEx. Maybe Antonietta, while Colin's sorting out his audio. Do you want to go ahead?
Sure. I think there was also Ming. I don't know if it.
Oh, okay, Ming. Sorry, I didn't see.
Can you hear me well?
Yep.
Yes.
Thank you for the very nice talk. So you mentioned this, the timing, location of the convection organization. That's very challenging. So what should we expect in terms of the model evaluation? Is that something inherently unpredictable? We need to run a large ensemble, in order to characterize the model error, or that's something really related to the model ability to capture those kind of organization?
I guess my quick answer, and I'll pass it to Rosie in a minute here, that one of the things we're looking at in that 40 and 20 member ensemble is in fact the variability of how the different members placed the convection and how accurate they were with respect to the storm modes to map onto our PRECIP framework. Talking about the MPAS part though, Rosie, maybe you want to jump in and answer that question. That was Rosie's slide, so I'll have her answer your question.
Sure. Yeah. So for the first portion about the location and timing of convective organization, I would say that the models were impressively good at telling us that it was going to rain on a day. But when it came to the timing, at what time during the day, was it 1 p.m., was it 3 p.m.? Some of them ensemble members from the convection permitting ensemble as well as MPAS were sometimes a little too late or sometimes a little too early. And also in terms of the location, because we had a very high resolution radar domain, it was pretty difficult to say we're gonna point the radar in this direction because we think that's where the storms will develop. With respect to what we see in the forecast, a lot of the times we just had to wait until the storms started and then shift the focus there. We just knew we had to be on alert because the models were hinting at convection happening on that day. And I'm sorry, I missed the part about the MPAS forecast. Would it be possible to repeat that part of the question?
I did not specifically ask the question about the MPAS, but just in general, the model. I guess one follow-up question is some of these quantities is just the emergent quantity of the model. So how can we connect to the parameterization, since that's where we can make some change to improve the model? So you mentioned this, for example, vertical shear microphysics and also orographic. What part of that, at least in this convective permitting model, is parameterized? What part is, it's just the model explicitly resolved? I guess like the vertical wind shear and orography, that's probably already just explicitly represented. Maybe it depends on model resolution. But from the parameterization point of view, for example, should we strive to parameterize convection organization? Some people, put this into the model, try to represent the convection organization. I'm not sure if that's a right approach towards this, since that can get very complicated, not necessarily improve the model results. Or just simply we should go to high resolution. It's more, yeah, broad.
Should I comment on this, Kristen?
Sure, go ahead. I have one comment after you're done.
Okay, yeah, very quickly, yeah, fully agree with you. It's very difficult to discern what can we correct, what can we not, right? Something that we're exploring is the possibility that even 3-kilometer grid spacing, which is what we use with both WRF and MPAS, may not be truly convection resolving. We call it convection permitting. It's not necessarily convection resolving, but something exciting that we have is that we have the very high resolution radar data, and we're going to be comparing it against simulations with different grid spacings, and we're hoping that that will inform whether we need some sort of parameterization at grid spacings that are greater than LES scales, essentially, and what that parameterization should look like. Over to you, Kristen.
Yeah, just one comment. I mean, we've seen that some of the modeled structures seem to be a little bit more deeper and more intense than what we see in observations. I think this is a well-known issue with, convection permitting models. And so, looking carefully at the microphysics, we have really excellent data on microphysics from our radars, and connecting that to, some of the parameterizations and what they look like in terms of estimating vertical motion, both in the presence of orography and over the island where there's very little topography. These are some things that we've noticed, at least in my research team. So, but yeah, there's a lot of work to do, and we just collected these observations. So we're excited for, anything we can do as well to help, your committee and the things you're thinking about. We're happy to take those into consideration.
Great, thank you very much.
Colin, do you want to jump in?
Well, can you hear me now?
Yes.
Oh, okay. I had to call in, so I have no clue what's going on here. Great talk. Thanks, Kristen. This was super interesting. I have a couple questions. One, I think, is about the modeling side of things, so maybe I'll ask that now, which is, you mentioned CM1. Could you elaborate a little bit on the plans, especially from like the process-oriented kind of side of things? What are the plans to use some of the data, or maybe experiments you guys are thinking about with CM1?
I can take that. So the plan, and we're making good progress on this, is that the domain principle is about, or the good data range is about 150 kilometers or so. So we have set up a model domain with it's like a box 150 kilometer by 150 kilometer, and we're running that, initializing it with an observed sounding, the daily average from the July 29 case that Kristen mentioned. That was a moisture surge day. We're initializing the LES simulation with that sounding, and we have simulations going all the way from 1 kilometer down to 50 meters. The idea is not to simulate that day, because, as you know, LES is, as with CM1, we can only produce idealized simulations. But we run the simulation for about 100 days with the large grid spacing with 500 meters. And then from that, we initialize the LES simulations. We're running them for a couple of days, and then we're gonna compare the statistics of the updrafts, of the reflectivity, the vertical structure of clouds and water vapor and other quantities against the vertical structure that we get from both the soundings at Yonaguni and the radar data, the SEPL radar data over Japan.
All right. Well, thanks. Yeah, I was actually going to say, that could be a really interesting bridge between some of the things you were discussing with the MPAS-A, even with the 3-kilometer runs, and really getting into that kind of 50 meters kind of regime. I think there could be, I don't know, I'd be really curious to see what comes out of that. That should be really fascinating. And then my other question actually was kind of a little bit off the wall, but you mentioned using hydrogen for the balloons. I was just curious if there was any regulatory issue with this. Did you just go we're going to buy a bunch of hydrogen canisters and launch balloons with hydrogen? Or, what needed to be done as far as a field campaign to get that trade-off?
Yeah, that's a great question. I mean, we dealt with a global pandemic, and one of the biggest challenges we had in the real-time observations was actually we couldn't actually order helium. It was not possible. And so actually, operationally in Japan, they actually use hydrogen on a regular basis, actually, to launch operational soundings from Japan. And so we were working very closely with the Japanese team. I think actually there's a slide that I showed where everybody's wearing blue suits. So we had a requirement that everybody wore a particular type of outfit that was low static inducing, right? So you're worried about static electricity charges and, potential fires and things like that. So we had, headgear and basically an outfit that was standard from the Japanese team. And because we're in a really moisture rich environment, the likelihood of static electricity was pretty low. If you're in a dry climate like Colorado, where I am here, static is everywhere. So it's a much bigger issue. We used helium here, of course, when we did our PRECIP 2021 campaign. But there are some safety documents that we did use in training our team, basically from our Japanese colleagues. But with helium shortages and the cost of helium, and it might be something that we should maybe consider if we can do it safely in the future. So I'm happy to share more details if you have any questions, but that was a really particularly challenging aspect that we were able to solve using hydrogen. But yeah, we just ordered hydrogen and had it shipped to the island. So.
Yeah, no, that's really fascinating. I mean, I've heard quite a bit about the helium shortage. I mean, to the point where, like, for my kid's birthday party, we couldn't get helium for balloons and stuff like that. So it's kind of, that's kind of been one of the, I don't know, looking back at like dirigibles and things like that, you're always told don't use hydrogen. But that was an interesting nugget. But I know Antonia has had her hand up for a while, so I don't want to keep prattling on.
Go ahead, Antonietta.
Okay, thank you. Very nice presentation. Thank you to both of you for being here with us. So I'm a physical oceanographer, so this question may be a little naive, but you mentioned at the beginning of your presentation that kind of one of the approach that you were using was meant to assess the universal aspects of the extreme rainfall problem. And so I was wondering, like, you chose this area to do your experiment because it's a very moisture-rich area. But how unique, how universal can the results be? Like, how much the specific characteristics of the area that you have chosen can be just unique to that area and maybe not applicable to to extreme rainfall in Colorado or in Western California or, in other regions? How can you extrapolate to these other areas?
Absolutely. That's a great question. So when we designed our field campaign, so we had a very big flood here in 2013 that wiped out a lot of roads up to Estes Park and things like that. And one of the things, and I've studied heavy rainfall and flash floods in the past. One of the things that's always mentioned is that, for example, in Colorado or in South Dakota, where a lot of these big flash floods had happened, after people do research on these events, they say, okay, well, the number one thing we need is moisture, tropical moisture to come into the region from the Gulf of Mexico or from somewhere else or from the monsoon to basically provide enough moisture in this dry climate to sustain such heavy rainfall rates and extreme events. And so in our experimental design, what we wanted to do is we wanted to say, let's take moisture out of the equation. Let's say we go to a place where we always have enough moisture. There is always sufficient moisture in Taiwan, basically, to get rainfall. And so that was part of our experimental design, was to basically remove that one variable from the equation and go to a place that had sufficient moisture but doesn't always have heavy rainfall in all situations. The design also in a region with mountains, the Central Mountain Range of Taiwan, and also Yonaguni, that has almost no topography, we saw an incredible difference in the amount of rainfall that we received at both sites. A lot of times the CPOL team they were kind of like, where's our rain? And in Taiwan, we were inundated with rain because of the influence of the mountains. I will also say that by using an ingredients-based approach, where we're taking specific ingredients and saying, okay, instead of just saying, okay, this one particular storm type or this we're looking for this type of mode, we're looking at ingredients supporting a wide spectrum of events. So this will allow us to more accurately, extrapolate out to different types of events in Colorado, for example, that fit on that framework. We also were lucky that we were actually able to do a full 3-month campaign here in Colorado. So we have a direct comparison with a micropulse dial, with similar radar scanning strategies, with similar radiosonde frequencies. And so we actually are doing really careful comparisons between these two. That was a highlight of the, a silver lining, I would say, of the pandemic, that we actually were able to do basically 2 field campaigns to directly answer those questions. And we hope that with the ingredient-based approach, we can generalize it to more, other locations outside of the 2 places that we do have observations. So that's my general answer, but it's a really great question, and it was part of our experimental design from the very beginning.
Yeah, thank you.
Hopefully that answers your question.
Convincing. Yes.
Okay, great. Thank you.
Mike, I think you are up next.
Go ahead and let Hailong go. I want to be sure the scientists are asking questions first.
Yeah, I'll make it quick then. Yeah, thank you for the very nice presentation. Congratulations on the successful field campaign. So my question, I touched on the other side of the question. Min talked about the parameterizations. I was wondering about, so most of those observed heavy events might be related to like larger scale frontal systems or cyclones. I wonder, when you do the model forecasting, did you need to decide on which kind of analysis to provide the boundary conditions for you to make the forecast, or have you looked at whether there might be sensitivity for your model performance when choose one or the other kind of large scale boundary conditions to drive the model?
Rosamar, I don't know if you want to answer that. We did try different forcing data sets. We also had a really nice test period for our model frameworks because we had this 3-year kind of 2-year delay of the campaign, which allowed us to do 2 years of modeling out ahead of the field campaign. I don't know, Rosamar, if you have an answer to that. I think I can answer for the Penn State system, but if you have an answer for MPAS, go for it.
Yeah, sure. With the MPAS forecast, MPAS is initialized, as we call it, cold start. So we have to choose an analysis. So for MPAS in 2020, we used GFS, which is what was routinely used, but through some comparisons after the period, we were able to reach an agreement with ECMWF, and they kindly provided their initial conditions. And so we realized that inevitably the IFS, ECMWF IFS initial conditions were better, or at least made the forecast more accurate in the long run. So we decided then to swap to ECMWF initial conditions for the initial times. With the Penn State ensemble, it has its own data simulation system that was running from the beginning of the campaign until the end, but then the trade-off there was that in order to have a large enough ensemble and to have it repeatedly during the day, we needed to make the domain size. We needed to make some decisions about the domain size, and in hindcast we realized that the highest resolution domain was perhaps too close to Taiwan, which might have been part of the reason why some of those ensemble members were producing too much rainfall on the eastern side of the slopes of Taiwan, potentially because the boundaries were being fed by the large scale rather than the convection permitting resolution domain.
Thank you very much.
And I also know that Yunji is doing a comparison. He did one version over Colorado with and without satellite radiance assimilation. So we're also looking at the impact of that real-time satellite radiance assimilation into the representation of the systems. So there's ongoing work looking at the decisions that we did make and how well our models performed in hindsight as well.
Great.
Thank you. Thanks for the question.
So yeah, I'll hop in here. I see we're coming up on our hour. So I've got 2 questions. The first is more the science, on the science side. The second is more programmatic. So the use of OSCEs to inform your field campaign design for your placement of observation systems. How successful was that then? So you showed us, that how you use the information to cite additional observational platforms in kind of that shadow region on the east side of Taiwan. How did that pay off? And are there any lessons that you might be able to share about the value of using those OSCEs and capturing that for the broader community as a technique that they might want to employ prior to going to the field?
Yeah, that's a great question. I mean, I had that one example from that one case. We looked at several examples of across the different modes of systems that we were looking at in that PRECIP framework. And we actually very carefully designed our radar scanning strategies to be a little bit more climatological, so we could capture more of the climatology of the region. There have been field campaigns in the past where, people are just scanning like crazy over the thing and it's moving. But if you want to do long-term statistics over a region, strategies like that struggle to actually capture like variability on broad scales. And so we wanted to design not only to capture a spectrum of modes, but also to get that climatology. And part of that, we were using the TRIM work that I was showing you, some of those frequency maps of where these objects are occurring, to make sure that when we put those radar sectors and the different RHI slices in different places, that we were actually slicing through places that would see those different modes that we were interested in. So I would say as a general strategy, it was really successful. It made it so that our radar scientists and our modelers and our leadership team, we were all talking to each other before we submitted the SPO EDO. So that everybody was on the same page of what types of observations we were hoping to collect, how we designed our scanning strategies to collect the observations we wanted, and then also, what we get out of it. We would actually have a preview of what we actually may see in terms of the data, filling any gaps that we might need to do that. So I think it was generally successful. We probably could have done more of that on the front end, but I think we did more than any other field campaign I've been a part of, and it was actually really a nice exercise to have that broad scale discussion across the team, getting everybody on the same page. I think that was another outcome from that.
Did it also help then set the stage for some of the modeling experiments following? Because you've already done some of the preliminary runs kind of in this simulated space versus the use of the actual observations that were taken. So did it help to engage on the front end the modeling activity for that purpose, to have them there to uptake the observations post-field?
Yeah, I would generally say yes. Like I said, we were already doing modeling in front of when we even submitted the proposal. We were designing and thinking about domains and things like that. And then due to the pandemic, we were able to do a lot of testing, actually, even before we got out there in the field. So, integrating our teams together and thinking about this on the front end, I think I would suggest teams try this, try something like this, because it really got everybody on the same page. We were talking all, from the very beginning, and I think it did set the stage for these great observation and modeling, interactions and collaborations that we.
Yeah, I think as you think about your publications, right? If there's a collection of publications or a post-field summary piece, that you think about highlighting that aspect and helping to promulgate that thinking within the broader community. If this is really one of the first times that the strategy has been developed using the models before going to the field in that way.
Okay. Yeah. Thank you. I appreciate it.
Sure. And I'll stop there. I had another program question, but we're at time.
Yeah. Sorry, Mike, conscious of the time, and I know lots of people have had to leave, and Kristen and Rosimar, I don't want to keep you any longer, but thank you so much. That was a wonderful talk and a great discussion afterwards, and looking forward to seeing more of your results.
Thank you for the invitation, and I'm happy to answer. If anybody has any questions, please feel free to email me. I'm happy to have further conversations offline. So thank you again for the invitation.
Thanks, Kristen.
Thanks, everyone.
Thank you.
Bye-bye.
Bye.
Bye.